Hello everyone. Today we'll talk about the solution to the problem valid arrangement of pairs. Here we're essentially given a list of dominoes. Those dominoes cannot be rotated, so they have a left and right end, let's say. And we want to put them in a line correctly. Any such arrangement is okay. And correctly means, of course, as in dominoes, that whenever two dominoes touch, their appropriate sides have to have the same number. It's easy to see when thinking about how to model this problem that this will probably be a graph problem, because this is something that looks like an edge, and indeed we can imagine that there is a number, some number we're starting with, this is the first domino, and some number will end with at the last domino, and any domino that we're given allows us to take a number and move to a different number. So for instance, if our current chain ends at number 4, then we can put any domino that has 4 on the left and something on the right, let's say 8, then we have an edge from 4 to 8, because when we have a chain ending at a 4, we can transform it into a chain ending at an 8. And it's good for us that those are edges that we have to visit, because we want to visit all of our dominoes, all of our edges. And if you're maybe familiar with the basics of graph theory, you know that finding a path or a cycle that visits every node is typically pretty difficult. It's called a Hamiltonian path or a Hamiltonian cycle. However, finding a cycle or path that visits every edge exactly once, it's easy, and it's known as the Euler path. So essentially this problem asks us in a roundabout way to find an Euler path in a directed graph. Now, if you're not familiar with algorithms for finding the Euler tour, Euler path, then it's something that you probably have to read up on, because they can be quite tricky. The basic idea is that we can essentially, well, first of all, whenever we have a situation where we don't know if it's a cycle or a path, we can easily decide, from the mathematical perspective, for a graph to have an Eulerian cycle, every node has to have the same degree of, the same in degree and out degree, so the same number of edges that enter it and leave it, which means that it has to appear on dominoes the same number of times as a left and as a right value. It's easy to see why, because of course whenever we enter a value we have to leave that value, and we only use a single edge once. And for an Eulerian path, so something that we're interested in our solution, we can either have the same thing, so everything has the same in and out degree, or we have one vertex that has out degree 1 greater than in degree, and another that has the reverse, in degree greater than out degree, and those will be the starting and the ending vertex. So this is what we're finding here based on degree, which is the difference between in and out degree. We find the starting vertex like this. And if we don't find a starting vertex, we can take any vertex that we want. So those are the basics. And the algorithms for finding Eulerian cycles, I guess the high-level idea is that we can essentially do whatever we want. We can go in whichever way we would like to go. And at some point, we're probably not have the possibility of going anywhere further. So we'll find some cycle, or maybe some path, but the problem is that it might not be the whole Eulerian cycle or path. Some edges might have not been, dealt with. And the idea is that we can look at any vertex on our path that still has a neighbor that we can visit, because that vertex has to exist, and we can simply start another Eulerian cycle from that vertex. And after we return to that vertex, we can just put that thing in the middle of the path or cycle that we're building. And we do that for as long as there are any neighbors. And the tricky part is the implementation, because this high-level idea sounds, in my opinion, pretty difficult to implement, but it's possible to do it in a brief way. So if you're interested, you can read up on it on yourself. So I'll assume familiarity with the concept, and so the implementation is to remember the graph, remember the difference between in and out degree of every vertex. We go through all the edges and remember the appropriate values. We have a starting node again, either as the one that's defined because we have a path, or any node if there is no defined starting node. Here we don't have to verify the condition for Eulerian path because the inputs are generated such that a path always exists. And now res will be the path that we're building. At the end we'll have to reverse it because we're building it in this recursive fashion, and of course we just return them again in the form of dominoes at the end. So just the previous and the next value. And here is the implementation that's very short. While there are still some nodes that we have yet to finish visiting, we look at their neighbors. If there are no neighbors, then we are done with that vertex and we can add it finally to our result. Otherwise, we take the neighbor of our last vertex on our tour, we take that neighbor and we push it into the current list of vertices that we're looking at. So this is essentially the implementation of that idea of branching out and doing auxiliary cycles and joining them into one big cycle. You can see that the code is quite easy, but how it corresponds to that idea might not be trivial. But this is something outside the scope of this solution, because an Eulerian cycle is a very general problem that appears in multiple scenarios. And essentially, we can assume, especially if it's a hard problem, that the person solving it is familiar with it. And if you're not, then this is a nice opportunity to read up on it.